All right, so we're talking about inverse functions today. An inverse function is a function where the input becomes the output and vice versa. And so like here, if we're looking at this function machine or whatever, if we have a function f, we have an input x and it spits out a y. And so we're kind of asking the question of, can we do that backwards? And if I put a y in, can it give me an x? And the answer is sometimes. Sometimes. And so an example of a type of function like this are something probably familiar to you, the conversion formulas for Fahrenheit to Celsius and vice versa, right? So here we input Fahrenheit and then the output is the Celsius. And here it's the opposite. So here we could actually switch the input and output and input a Celsius and we get an output in Fahrenheit, which is fairly useful, right? Um, And so a little notation for you. If we have a function f of x, we denote the inverse like this. And we read this f inverse of x. This -1 is not an exponent. It is just part of the notation. And again, we read it inverse. It is not an exponent. So the first thing we're going to talk about is finding the inverse function as a set of ordered pairs. And so let's say I give you this function that's defined with, a set of inputs and a set of corresponding outputs, which is nothing strange. We've seen this plenty of times. Well, what is the domain of this function? Well, it's just going to be the x values. So 2, 3, and 4, those are the inputs. And the range are simply the outputs of the function. So this would be 5, 6, and 7. Right? So nothing too crazy yet. So what would the inverse of this function be? Well, it would just be a set of ordered pairs, except for we change the output to the input. So this would be 5, 2 instead of 2, 5. This would be 6, 3 instead of 3, 6. And this would be 7, 4 instead of 4, 7. So again, all we've done is swapped inputs and outputs to obtain the inverse. Swapped inputs and outputs. Okay, so now let's go again. Let's state the domain of the inverse. Well, domain is the inputs, and so that's these guys. Right? So that is 5, 6, 7. And then the range is 2, 3, 4. And you can notice here, notice the inputs for the function f have become the outputs for inverse and vice versa. So we just mainly swap those out. And so as a result of that, is this really fun sentence to deal with. The domain of a function is the range of its inverse, and the range of a function is the domain of its inverse. And that very interesting tongue twister is what we just saw here, right? Just a swapping of the inputs and outputs. So the domain of the inverse is the range of the original function. And again, so we just illustrated that there. And now here's this really complicated diagram to make it difficult. So example 1, the domain, let's say, of some function f is 1 to infinity, and the range of that function is negative infinity to negative 2. Find the domain and range of the inverse. Well, remember, the domain of the inverse is the range of the original function. So the domain here would just be negative infinity to negative 2. And the range would just be the original domain. So we just swap. Not too bad. Example number 2, if for this one-to-one function f of 2 equals 4 and f of 5 equals 12, what are the corresponding input and output values for the inverse? And so what I'm looking for is f inverse of something equals something else, and f inverse of this equals this. So remember, we're just swapping inputs and outputs. So the input here is 2, so it's going to become the output here, and the output becomes the input. We are just swapping steps. So this would be f inverse of 12 for this function would be 5 in the original function. f of 5 is 12, f inverse of 12 is 5. So we're just going backwards and forwards. Here, given that f inverse of 6 equals 2, what is the input and output value for the original function? So once again, we just swap inputs and outputs. So f of 2 would be 6. All right. So now let's do that using a table. Same idea. This table is going to show the distance in miles that cars traveled in t minutes. Right. So in the normal function, t minutes is the input and the output is the miles, or f of t. So what is f of 30? Well, for an input of 30, we obtain an output of 20. And that means that, in 30 minutes, the car travels 20 miles. Straightforward enough. And now we're going to go backwards. We're going to say, okay, what is f inverse of 70? Well, if the input is 70, the corresponding input is 90. And so it takes a car 90 minutes to travel 70 miles. So really, we're still talking about the same exact scenario. It's just whether I give you miles or minutes. Right? So now let's talk about finding and evaluating an inverse from a graph. So I want you to use this graph to find g of 3. Well, that's just, this is g of x. So we just say, okay, input 3 gives me an output of 1. So input 3, output 1. So g of 3 is 1. So what is the inverse? Remember, here it's the input, but here it's the output. So g inverse of 3 would be here. So what do I end up with? Well, that would just be 5. See how we went backwards? So this idea of inverse is we go backwards from the way we went before for the regular function. So I started here, and this is my output. And then when we're finding using the inverse function, we're going to go here and then find this output, which is the original input. So again, just this idea of swapping directions. So now we'll get into the actual real deal stuff that we'll be doing. A lot of that was just kind of conceptually something you'd have to understand, but really there aren't a whole lot of calculations required. So let's say that two functions are inverses of each other. Let's call one f and one g. And then the composition of those two functions should just equal x. So either f of g of x will equal x or g of f of x will equal x. And so remember the composition of functions from a couple sections ago. That'll come in handy here. And all this notation means is f composed with f inverse is x, which we said here f and g are inverses. So that's exactly the same thing with a different notation. So let's take a look at an example. Our f and g inverses. And so in order to determine this, I'm going to compose f and g. So I'm going to find f of g of x. And so remember what that would look like would be I would have this shell created with f. The input for the function f is actually the function g. And so now we'll just do some algebraic simplification, right? So these twos should cancel. That's going to leave me with x minus 1 plus 1. Negative 1 plus 1 is 0. So we do end up with just x. So the composition of f and g is in fact simply x. And so we say yes, they are inverses. So if when performing that composition you end with x, then they are inverse. And to kind of give you the graphical representation of what inverse functions look like, and this is a lovely way to check your algebra on Desmos, the graph of inverse functions reflects across the identity line, which is y equals x. So if you're graphing that, this line is y equals x. We call that the identity line. And this red function is the 2x plus 1. and the blue function is x minus 1 over 2. Notice they are a perfect reflection across that line. And if that is what it looks like graphically, then we do say that these two are inverses of one another. So that's one way we can check our work. It's by seeing in Desmos if they are in fact a reflection over that identity line that you see here. Okay. So let's check another one. So our f and g inverses. So I'm just going to be like, all right, man. So let's do f of g of x and see what happens. So we'll make a shell with f. And the input for the function f will be g. So this will be 1 over x minus 2. Well, I can drop these parentheses. And that's just 0. 2, negative 2 plus 2 is 0. So then I have 1 over x. And so I'll multiply by the reciprocal here. And I just, again, end up with x. So yes, they are inverse. And you could, again, always confirm that with the graph if you wanted to. All right, so now we see a change of notation in example 8. So I asked a minute ago in words, are they inverse? And this says, does the function g equal the inverse of f? And so that's another way of asking, are g and f inverses? And so we're gonna conquer this in the same way, except for this time, I'm going to do g of f of x. You could do either one. Sometimes the algebra is easier one way or the other. So in this case, let's see. It doesn't really matter. So that'd be 1/3 x, and we're going to plug in the function f as the input for the function g. That is not going to simplify to x, and so these are not inverse, because this is what we end up with, and that doesn't simplify really any further than x cubed over 3, and that's definitely not x. So you kind of have to be confident in your algebraic manipulation skills to really say that if it's not. It's a lot easier to say it is because we arrive where we need to get. But let's do this one again. Let's do g of f of x. And so we'll have a shell g. And the input for the function g will be the function f of x. And so we'll have, x minus 1 cubed here. But remember, the cube root is the inverse of the third power. So these are just going to kind of cancel each other out. And I'm going to have x minus 1 plus 1, and look at there, all done. So yes, these are inverses. Once again, you can go to Desmos, plug those in, see if they reflect over that y equals x line. And if they do, then hooray. All right, so that's verification of inverses. Like if I give you two functions, are they inverse? You'll do the composition. And if you get x, the answer is yes. If you do not get x, the answer is no. So this is something that we're going to pull a little bit from earlier in chapter 3. So when we're finding the inverse of a function, the first thing we have to understand is that the function must be 1-to-1. And remember, that means it must pass the horizontal line test. And it also means that each input should have one and exactly one associated output, right? So that's what we mean when we say 1-to-1, one output for one input. And so if that happens, then we run into the issue of we have to restrict the domain, right? And so here's a really good example of that. So if we look here, we have x squared, and normally the inverse would be this. And so you can see where we run into an issue, right? If the outputs of this function are the inputs of this function, then we're fine, because this has to be positive, right? Because this has to have a positive input. So with all these over here, it's not going to work, because if I take the inverse of the whole thing, then the reflection will look like this. And notice, this is not a function. It fails the vertical line test. So the square root of x is not a function if we purely put it over here and reflect it across this y equals x line. So what we're saying is we have to restrict the domain of this function to make it 1-to-1, because x squared is not 1-to-1. because let's take a look. The input 2 has an output 4. The input -2 also has output 4. That violates the rules for a one-to-one function. We can't have that. So what we have to do is we have to restrict the domain of x squared to make it one-to-one. And the way we do that, and the key point here, is a one-to-one function, 1 to 1, are either always increasing or always decreasing. So really what I want to do here is I want to take this part of x squared, right? That is the part of x squared that is always increasing. And so I'm going to choose that one. And so I'm going to restrict the domain of x squared to 0 to infinity, right? Because that ensures, because on this domain, we are always increasing. That's why in some of your previous practice problems and in your homework, I said, what are the domains where this is increasing and decreasing? And it was kind of preparing us for this. So I've chosen to restrict that because otherwise it would not have an inverse. But if we do restrict the domain to 0 to infinity, that part of the function, x squared restricted to this domain, does have an inverse, which is the square root function, square root of x. And so that's perfectly fine. So all this time, you just never knew that we were doing all this special stuff with x squared when we were taking the square root, and we really were. So remember from previously, the domain of a function is the range of its inverse, and the range of a function is the domain of its inverse. So kind of what we're saying here, let's kind of pick that apart in terms of the x squared and square root. So a function, let's call it f, our function is x squared. And what is the domain and range of this? So we said the domain is this. And the range is already this, right? It's always going to be positive. And so f inverse is going to be the square root of x. And so if the domain of this function, if the domain of the original function is the range of its inverse, that's the only way that's going to work, right? Because the output of this function is always positive. Because the input must always be positive. Hence, that's why we have to restrict the negative values here, because otherwise it's going to mess up the domain of this guy. And so I say all that to say, let's talk about the actual types of problems that you're going to have to do. So the type of question you're going to see is find a domain on which the given function is one-to-one. Then find the inverse of f restricted to that domain. And so this part entails where is it strictly increasing, right? Let's restrict it to where it's strictly increasing. And this is where you have to have knowledge of your toolkit functions, right? So we're going to have to go back and find this in just a little bit. So let's take a look. When we are working on a question like this, the first thing we need to do is find the inverse of a function given its equation. And so let's go back to this example. We already know these are inverse, but let's check. Let's say I want to find f inverse. Here are the steps. First, we're going to write this in terms of x and y. So this is x equals 2x plus 1. Excuse me. Interchange x and y. So this becomes an x, this becomes a y. And now solve for y. So this would be x minus 1 over 2 equals y. And so this, our result is going to be f inverse, which is exactly what we see here, right? We already determined in an earlier example that this function is the inverse of 2x plus 1, and that's exactly what we found with this procedure. So that's your first step in the procedure. Let's do a couple of examples with those. So find the inverse of this function. So remember, we're going to first write it in terms of y instead of f of x, 2 plus square root of x minus 4. Then we're going to interchange x and y. Then we're going to solve for y. So this would be x minus 2 squared equals y minus 4. And then we would just x minus 2 squared plus 4 equals y. And so this is f inverse. Let's do it again. So to find the inverse of this function, again, I'm going to write it in terms of y instead of f of x. I'm going to switch x and y. And then I'm going to solve for y. So the first thing I'm going to do is subtract that 4. And I'll have this. I'm going to eliminate the denominator by multiplying. And then I'm going to have to get all of this hashed out, right? So I'll have to do xy. I'll FOIL it or whatever you call it, repeated distribution. X times y is xy. And this is minus 3x minus 4y plus 12 equals 2. And let's recenter ourselves and ask ourselves what we're doing so we can figure out what to do. I'm trying to solve for y. So let's get everything with a y by itself and move everything else to the other side. So this will be xy minus 4y. And then I want to move this over so it's 3x. This will be minus 12 and the plus 2 stays. Now let's factor out a y. X minus 4. This is 3x. This will be minus 10. Well, guess what? Now I can just divide by everything that isn't y, and I'll be all done. And this is f inverse. All right, let's go back and look again at a question similar to one we've already answered. So suppose the domain of a function is this. Well, not similar to, exactly the same. So, and the range of the function is this. So find the domain and range of the inverse. So remember, if this is the domain of the original function, it's the range of the inverse. And if this is the range of the original function, it's the domain of the inverse. We just switch swap. We swap domain and range between the original function and the inverse. All right, so now let's actually answer the entire question that we've been building up to over this whole last section. So find a domain on which the function f of x equals quantity x plus 3 squared is 1 to 1. Write the domain in interval notation. So the first thing I need to do is I need to find out, where is this guy strictly increasing? Where is it increasing? Well, I mean, using function transformations in the toolkit functions, it shouldn't be terribly difficult. Where is it increasing? So in my mind, you can see me work it out. I know that x squared starts at 0, 0. That's so ugly, but whatever. And I know that this is going to precipitate a shift left 3, right? So this will become negative 3 instead of 0. And my new function is here. So where is this function increasing? Well, here and up, right? So the domain on which this function is 1 to 1 is the domain where it is strictly increasing, which would be from negative 3 to positive infinity. So there's the domain and interval notation. And now I'm going to find the inverse of f restricted to that domain. Well, guess what? We already did that too. And that's the thing that I do where I'm like, okay, instead of f of x, I'm going to write y equals. I'm going to switch x and y. All right, we just did this, right? And then I'm going to solve for y. So this would be the square root of x equals y plus 3. The square root of x minus 3 equals y. And look, so here is the inverse function that I've requested. So that's f inverse. So notice we just kind of put the two things together that we've already been discussing. We kind of molded all of them into a single thing in this type of problem. So, and just to give you a visual, I created a graph in Desmos where you could see what we actually did. This is the original function. The solid red line is where I have restricted it to be 1-to-1 because that is the location where it is strictly increasing. And we can see that the domain where it is strictly increasing is in fact from -3 to positive infinity. I then graphed the inverse I found, root x minus 3, and that's the function seen in blue. And so if you recall what I said about testing with a graph to see if you found the correct inverse, look at the solid red and the solid blue. They are in fact reflections over the dotted y equals x line. And so they are the correct inverses. So I did that problem correctly, and that is how I checked my work. And really that's that for inverses. And so feel free to pause, go back, print this screen, annotate the notes, and then we will work some problems together in the next class. And that'll be all for today. Thank you.